Good day, doctor. Today, my group mates and I will be presenting on various types of corrosion and different ways that can be used in corrosion protection. Corrosion mainly can be divided into three main groups. First is uniform corrosion, second is localized corrosion, third is combined effect and mechanical factors and corrosion. So under localized corrosion, there are 6 types of corrosion, while under combined effect and mechanical factors and corrosion, there are 4 types of corrosion. First, we are going to see uniform corrosion. Uniform corrosion is a type of corrosion where the corrosion occurs with an equal intensity on the entire surface of the metal, where the metal corrodes uniformly on the all over the metals. So based on the example here, we can see that the intensity of the corrosion is uniform on the surface of the metal. Thus, we can conclude that this is a uniform corrosion. Now we are going to see localized corrosion. So under the localized corrosion, we are going to see pitting corrosion. Normally, the metal or alloy has a passivating layer. So when the passivating layer fails to protect the metal or the alloy, a small pits or holes or even a bigger holes can be formed. So this is the result from the pitting corrosion. Next is crevice corrosion. Crevice corrosion occurs at locations where oxygen cannot freely circulate, such as tight joints, under fastener heads, and in other circumstances where the pieces of metal are in close contact. So, the chloride salt, pollutants, and moisture from the environment accumulate in the crevice. The environment inside the crevice becomes depleted of oxygen, enriched in chlorides, and acidified, which promotes the breakdown of the passive film and anionic dissolution. So from here we can see where the pieces of metals are in close contact, the concentration of oxygen will be lower comparing to the environment at outside. Thus, the crevice corrosion occur at the inner part.
Hello and good day to Dr. Haswan and my fellow groupmates. So I'll continue with localized corrosion. Firstly, I'll touch on galvanic corrosion. Galvanic corrosion, in other terms, it is also known as bimetallic corrosion, which is an electrochemical process whereby one metal corrodes in preference to another metal that it is in contact with through an electrolyte. Galvanic corrosion occurs when two dissimilar metals are immersed in a conductive solution and are electrically connected. So, for example, if aluminium and copper are connected and immersed in an electrolyte, so in this case, aluminium is the more reactive metal, the more electropositive compared to copper. So aluminium will tend to undergo oxidation and gives up electron readily. So aluminium will become the anode, which is the negative electron. And finally, the aluminium will corrode more quickly, while the copper will receive protection. Next is intergranular corrosion. Intergranular corrosion occurs when the grain boundaries in a metal form an anode and the interior of the grain acts as a cathode. This type of corrosion is a common problem in stainless steel. However, it can also occur in other metals. In stainless steel, the problem occurs after the metal is heated to between 425 degrees Celsius and 870 degrees Celsius. During the heating, the chromium in the stainless steel reacts with carbon in the steel and forms particles of chromium carbide at the grain boundaries. The region near the grain boundaries become depleted in chromium. This means that the region around the grain boundaries are no longer protected by the chromium passivation and therefore corrode intergranularly. Third is selective corrosion. Selective corrosion occurs when one element or constituent of a metal is selectively corroded out of a material. It is referred to as selective leaching. The most common example is the dezintification of brass. After leaching has occurred, the mechanical properties of the metal are obviously impaired and some metal will begin to crack. Selective corrosion may occur in a single phase and also in multi-phase alloys. Finally is on filiform corrosion. Filiform corrosion is a special form of corrosion that occurs under some thin coatings in the form of randomly distributed thread-like filaments. Filiform corrosion is also known as underfilm corrosion or filamentary corrosion. Filiform corrosion occurs on metallic surfaces coated with a thin organic film that is typically 0.1 mm thick. The pattern of corrosion attack is characterized by the appearance of fine filaments emanating from one or more sources in semi-random directions. The filaments are fine tunnels composed of corrosion products underneath the bulge and crack coating. So that's all for localized corrosion.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nourizati Maisara binti Muhammad Hanafi. I would like to talk about the combined effect of mechanical factors and corrosion. The first one is the stress corrosion. Stress corrosion is the combination of applied tensile stress and a corrosive environment. Stress corrosion may result from external stress such as actual tensile loads on the metal or expansion or contraction due to rapid temperature changes. Stress corrosion may also result from residual stress imparted during manufacturing process. The second one is the corrosion fatigue. Corrosion fatigue is fatigue in a corrosive environment. It's because of mechanical degradation of a material under the joint action of corrosion and cyclic loading. Next is the erosion corrosion. Erosion corrosion is a combined action involving erosion and corrosion in the presence of moving corrosive fluid or a metal component moving through the fluid, leading to accelerated loss of metal. Next is the fretting corrosion. Fretting corrosion causes corrosion damage at the asperities contact surface. Damage is induced under load and in the presence of repeated relative surface motion as induced, for example, vibration.
Hi, I'm Faris. So for the cavitation corrosion, this is often occur when the corrosion and the pressure form breaking of gas bubble form in liquid that we also known as cavitation. This also often occur in place where high velocity liquid flow and the pressure changes are encountered, such as the ship propeller and hydraulic turbine. Next part is the microbiological corrosion. This is caused by deterioration of metallic materials that are caused by the presence of the microorganism. These activities or the presence of microorganisms are included in the metabolic activities of the micro itself. This also can be found in the contaminated fluids. For the next part is the corrosion protection. First, corrosion protection that well known is the material selection. This material selection depends on metal and chemical composition of the metal. So the type of the protection are involving the marine environment, high pressure gas environment, dam environment, and also known as modified properties that we also familiar with the alloying. The alloying of metal are purposely to produce the corrosion resistant alloy. This modification of the metal can be found in the stainless steel, which can form a corrosion resistant properties. As we can see from the diagram, the alloy stainless steel are protected by the protective layer that is the chromium oxide. This can maintain the integrity of the stainless steel itself. For the next part is the environment modified. This also involves the controlling of the environment. What we can control? We can control the humidity, we can control the removal of oxygen, we can control the pH, pressure, contaminant, and etc. Instead of we control the environment, we also can use the inhibitor. What is inhibitor? The inhibitor is purposely to form a barrier that reduce flow of ions and electron across to a very low values. This also include the separated into cation and iodine mixed inhibitor.
Assalamualaikum and hi doctor. I am Alia. Today I would like to present about the corrosion protection. So first, installation of protective coating over the metals. So the purpose is to isolate the metals from the corrosive environment. It has two ways for protective coating, which is first, coating or covering with more noble metal or better corrosion resistant properties, and non-metallic coating, which is inorganic and organic coatings. For metallic coating, it is coating with more noble metal. For example, iron coated with chromium, nickel, tin for decoration purpose. Next is coating of zinc in galvanized steel and coating of tin on iron for containers. And for non-metallic coating, it is non-metals are used as coating material in case of non-metallic coating. Common types of such coating are plastic or rubber coating. This involves application of a layer of the given polymer onto a substrate material. For non-metallic coating put over on a metal can be of two types, which is first, they can act as a physical barrier and bar access to the metal surface. And second is they can introduce a very high resistance into the corrosion circuit and drastically reduce the flow of electrons. So for non-metallic coating can be split into two parts, which is inorganic coating, for example concrete, silica, and ceramic. And second is organic coating, which is tar, paint, plastic, and others. Paint coating are considered the most practical and economical means for the corrosion protection. Paint is the most common protective coating applied. So next for corrosion protection is proper designing. There are a few key design rules that can be followed to help minimize or prevent corrosion. First, use more corrosive resistant materials such as metal that passivated. Second, remove aggressive species from environment. Add chemical to environment that inhibits corrosion. Separate the metal from the environment with a barrier layer such as paint. Next is remove crevices from design. Prevent galvanic corrosion by using compatible materials or electrically insulating dissimilar materials. And reduce T, which is low kinetics of oxidation reduction reaction. And lastly is use cathodic or sacrificial protection or anodic protection. And the last part for corrosive protection is impose an electric current. Impose an electric current can be categorized into two, which is cathodic protection and anodic protection. Cathodic protection is metal to be protected will be cathode, and anodic protection is metal to be protected will be anode. For cathodic protection is a technique to control the corrosion of a metal surface by making that surface become cathodic to the environment or the cathode of the corrosion cell. So cathodic protection can be achieved in two ways, which is first by connecting a more anodic metal into the corrosion circuit than the metal to be protected, which is galvanic protection or sacrificial anode. And second is by passing of an electrical DC current so that all areas of the metal surface become cathodic and therefore do not corrode. For anodic protection, when will we use the anodic protection? It is used when cathodic protection is not practical. So anodic protection is a useful corrosion control technique. Anodic protection only happen in strong acidic or alkaline solution. Specifically, in meta-environment conditions where active-passive behavior is demonstrated, anodic protection is usually effective. In practice, the meta-environment potential is held in the passive region by polarizing the structure in the electropositive direction, where the passive layer is more stable. So here we can see the difference between cathodic protection and anodic protection. For cathodic protection, the advantages can be used for all metals, installation cost is low and corrosion rate can be reduced to 0. And the limitation can only be used in weak to moderate environment, and operating condition must be determined by empirical testing. For anodic protection, the advantages can be used in extremely aggressive environment. Applied current is direct measure of corrosion rate. Operating conditions can be easily controlled and operation cost low. For the limitation, only applicable to active passive metals and installation cost is high. So that's all from us. Thank you.